Hi everyone. Our discussion for today is some additional properties of real numbers. At this point we've already talked about the closure property. Next we have three that are hopefully familiar to you, followed by two additional and final properties. So just a reminder, properties are facts that are always true regardless of the specific numbers chosen. So these properties are true for all real numbers, but when we're talking about sets of numbers that are not the real numbers, these properties may or may not apply. Now these next three do apply to any subset of the real numbers. So the first is the commutative property. And you have probably seen this one before. It works for addition or multiplication, and it's the property that lets you switch the order of numbers to flip them around and still get the same answer when you're adding or multiplying. So for example, we know that 3 plus 4 is 7, and that's the same answer as if we flipped this and added 4 plus 3. Same thing for multiplication. Now this is any real number. A lot of times we'll do whole numbers as examples, but this works also for fractions, irrational numbers, things like pi, anything like that. So I could do 1/2 times 5, and that's the same as 5 times 1/2. Alright, what about subtraction? Is subtraction commutative? So in other words, for all real numbers, is a minus b the same thing as b minus a? And I think you can come up with a counterexample to that one. Alright, what about division? Is a divided by b the same thing as b divided by a? So same thing there, you can probably come up with a counterexample to show that subtraction and division are not commutative. Now here's another interesting question. Are those two statements ever true? Right? Just because you can come up with counterexamples doesn't mean that you never have an example that does make the equation true. Alright, so that could be a second challenge or just something that's interesting. Try to come up with numbers a and b so that you do get the same number when you switch the order for subtracting and dividing. The next property is the associative property. And this is the one that allows you to, this time we're still switching an order. For commutative, we switched the order of the numbers. And for the associative property, we're switching the order of the operations, the order in which the operations are done. Okay, so sometimes you'll also see the word grouping attached to this property. We're changing the grouping of the numbers. All right, so this one says if I have 3 plus 4 plus 2, and if I add the 3 plus the 4 first and then the 2, that's the same as if I add the 4 plus the 2 first and then add the 3. Same thing for multiplication. We could do another example that's not whole numbers. We could do, let's see, 1/4 times 16 times 3. And here I've grouped the 1/4 and 16 together. That's the same as if I group the 16 and 3 together and multiply those first. Alright, what about subtraction and division? Are those associative? I'll leave this one for you to answer, but to check this, we want to know, is a minus, let's look at a minus b minus c. And if I put the parentheses in two different places, around the b minus c or around the a minus b, okay, are those two expressions the same? Okay, so you could try this out. Do maybe like 30 minus 10 minus 8, or try 30 minus 10, subtract that first, and then subtract 8. And you can come up with your own if you like. What about division? So same thing. Is it true for all real numbers, a, b, and c, that dividing b plus c first, dividing b divided by c first, is that the same as a divided by b first, and then divided by c? Okay, so try that out as well. The distributive property. I know you've seen this one before as well. Now this one is the distributive property of multiplication over addition. All right, so in other words, we have to have a number and then times, and then in parentheses a sum. Okay, and then we distribute that multiplication to the addition inside of the parentheses. All right, and this property says that that expression is the same thing as a times b plus a times c. Okay, here's a specific example from your textbook. This is saying 3 times the sum, 2 plus 4, is the same as if we distributed the 3 times the 2, distributed the 3 to the 4, and then did the addition afterwards. Here's a visual as well for why this works. This first expression, 3 times the quantity in parentheses, 2 plus 4, that's like looking at 3 groups of a sum, 2 plus 4, or maybe you could think of it as like 3 rows that are each 6 long. And you can see visually, if you just sort of rearrange or change the spacing between the blocks here, that that's the same as 3 rows of 2 plus 3 rows of 4. Okay, so looking at the whole long rows first versus looking at the 2s and the 4s first. Now, some tweaks on the distributive property. We can distribute from the left or from the right. Right, so let's do a right-hand example. If we had 5 plus 2 times 3, now you can write that 3 in parentheses, or you could use a dot for multiplication, or another multiplication symbol. So now when you distribute, it's being distributed from the right, so it goes on the right of each of those numbers. So this is the same as 5 times 3 plus 2 times 3. Okay. Now to check this, I should mention, let's work these out using order of operations, all right, to check and make sure that this works, at least in this case. Okay, so we're verifying, we're not proving. On the left, this expression is indicating we should do the parentheses first, 5 plus 2 is 7, and then do the multiplication. On the right, order of operations, we should do the multiplication first, and then go back and do the addition. All right, so that's the difference between those two. And if you needed to show that those two are the same, or like if you were giving an example or something like that, then you would need to show this middle step to show how these two are different. So don't just skip to the 21, because that doesn't really show the different operations. Are there distributive properties for other operations? So far we've only talked about the distributive property for multiplication over addition. We actually haven't even talked about multiplication and subtraction, but you've probably used this one before as well. So for instance, if we had 3 times the quantity 4 minus 2, is it okay to make this 3 times 4 minus 3 times 2? That would be the distributive property for multiplication over subtraction. And that one does work. It's a really easy proof to show this. Okay, so A times the quantity B minus C. First of all, I know that subtraction is just adding a negative, so I can rewrite this as B plus negative C. Okay. And now it's addition, so now I can use my distributive property for addition and make this A times B plus A times negative C. All right. And well, now I know this is A times B, and A times negative C, I know that's the same as subtracting A times C. All right, and there you have it. So we have, on the left, we have this expression with subtraction, and then I've showed that that's the same as this distributed expression with subtraction. All right, so we can go ahead and just assume that it now works for all examples with a subtraction sign in the middle. What about if I change the operation on the outside? Is there a distributive property for addition over multiplication? So in other words, is A plus, in parentheses, B times C, is that the same as, I'll put a question mark because we don't know, a plus b, okay, and then, so do that first, and then times a plus c. Are those two the same? Okay, so it looks different than your current distributive rule, but that doesn't necessarily mean it's not true. It could just be a new distributive rule. All right, so again, to check one way or the other, you would maybe want to plug in some numbers here. Is 3 plus 2 times 4, is that the same thing as adding 3 plus 2 first and 3 plus 4 first, and then multiplying those two together? Okay, and you can check yes or no. What about other systems than real numbers? Well, here's a fact about these first three properties. We say that any subset of the real numbers inherits some of these properties from its kind of like a larger parent set. Right? So any subsets of the real numbers inherit the commutative property, the associative property, and the distributive property. And that kind of makes sense. So, for instance, if I asked, are the natural numbers commutative? All right, well, for addition, like 3 plus 5 equals 5 plus 3. Well, we know that that works because they are real numbers as well as natural numbers, so they do have that property. I don't need to prove a distributive property for irrational numbers. Okay, because they're all real, I know that something like square root 2 times square root 3 plus square root 4, I know that I can distribute those square roots because that's a rule about real numbers. Okay, it works for any real number. Other systems than the real numbers. What about something that's not a subset of the real numbers? And it turns out yes. Okay, so we've talked about the imaginary numbers, and the distributive property will work for those. Same thing with commutative, associative, things like that. Okay, there are some systems it does not work for, some of these properties. Here's one. I don't know if you had matrix algebra before, but if you did, this may look familiar. Okay, matrices are just grids of numbers like this. They're displayed in brackets. Here's a distributive property for matrices. If I had like a real big long one like this, and let's say I'm adding here, and let's make this one different. How about 0, 2, 8, 3? Okay, so we won't talk about how this works, but the distributive property does work. You can distribute and multiply the matrices together before doing the addition. Matrix multiplication is not commutative, and let's see, matrix addition is commutative. Okay, so some of these properties do hold for other systems and some don't. All right, we have two more, the identity, and then we'll also talk about the inverse property. These are not inherited by the subsets of the real numbers. So if we look at just the set of natural numbers, for example, okay, this one doesn't necessarily have an identity property, but we'll focus on just the set of real numbers for this one. And here's the idea behind this property. We have two special numbers, 0 and 1, which are called the identity elements, and we know that 0 added to any number equals the number itself, and 1 times any number equals that number itself. Okay, as long as these numbers are real numbers. Okay, so that's what's special about the identity element. It's just preserving the value of whatever number you started with. Okay, so 0 is the identity for addition, 1 is the identity for multiplication. All right, so if you saw something like, could phrase this a couple different ways. If the question is what is the identity for addition, then the answer is just 0. But if you saw something like 5 plus 0 equals 5 and you needed to identify what property that was, that would be the identity property, because this is showing that you can add 0 to 5 and you still get the same answer, 5. All right, the inverse property. Within the set of real numbers, every real number has another number that can be added to it so that it equals 0, and every number has an inverse or a reciprocal that can be multiplied by it to get the number 1. So in other words, we're trying to get back to those special identity elements. Okay, so for addition, we want to find a way to combine numbers to get the identity element, and for multiplication, we want to multiply numbers to get the identity, which is 1. Okay, so we're first of all guaranteed that every real number has one of these things. Okay, now the one exception is the number 0. Okay, 0 does not have a multiplicative inverse. Okay, so in other words, if I put 0 here, there's nothing, no real number that I can put here, so that I will get an answer of 1. All right, so find the additive inverse of 2/3. So your answer, an additive inverse is just a number. So your answer should be what number gets added to 2/3 to equal 0? And the answer would be negative 2/3. Okay, so that's the inverse property. It tells us it's always the negative of the number that works. How about the multiplicative inverse of 2/3? So now this time we're asking what number do you multiply times 2/3 to get 1? All right. So we're told by this property that it's the reciprocal, and the reciprocal of 2/3 is 3/2. So notice if you multiply these, okay, then you're going to get in the numerator 2 times 3 is 6. In the denominator, 2 times 3 is also 6. And 6 divided by 6 is 1. All right, so the multiplicative inverse is 3/2. Now in this property box, they tell you the reciprocal is 1 over the number, and that is also true. So just remember that 1 over 2/3, or 1 divided by 2/3, is the same as 3/2 if you just flip the numerator and denominator. Okay. Let's do one more example. Okay, what if the question was find the additive inverse of 5 and the multiplicative inverse of 5? Okay, so it's asking what number, for additive inverse, what number do you add to 5 to get 0? And the answer is negative 5. For the multiplicative inverse, what number times 5 is equal to 1? So here it's the reciprocal, which is 1/5. Okay, just 1 over that number. And let's maybe do one more. I know I said 1, but we'll do 2. How about the additive inverse of pi and the multiplicative inverse of pi? Okay, so we're just going to go based on the patterns given to us in these properties. It's always the negative of a number, which is its additive inverse. So the answer should be negative pi. And then the multiplicative inverse of pi is its reciprocal, which is 1 over pi. Now we can check these. Okay, so we want to make sure, does pi plus negative pi equal 0? And that is true. That's like pi minus pi. So anything minus itself is 0. So that works. And then what about multiplication? Pi times 1 over pi, does that equal 1? Okay, well, this would be multiplying, this is like pi over 1. So multiplying, you'd have in the numerator, pi times 1 is pi. In the denominator, 1 times pi is pi. And then pi divided by pi, okay, they would kind of cancel. And that gives you 1 as an answer. So we're getting 0 and 1 as an answer, so these are the correct answers. Okay, and then I want to end with some examples of illustrated properties and see if you can pick out which property is illustrated. So here are the choices. We have, not in this example, but the closure property is always a possibility. We have the commutative property, we have distributive, associative, identity, and inverse. Okay, so in example A here, 6 plus 5 equals 5 plus 6. Basically, you're just checking to see what's different about the left side of the equal sign from the right side, and then match it up with one of the properties. So 6 plus 5, 5 plus 6, what's different? Well, it's the 5 and the 6, they've switched places. Okay? So it's the commutative property that says that you can switch the order of numbers like that and still get the same answer. In part B, 0 plus 3 is 3. This sort of just looks like a normal addition problem, but I'd encourage you to look, if that is the case, look for things like 0 and 1, and those are going to be clues that we're talking about one of these identity or inverse properties. So what we're saying in part B, this is trying to illustrate the fact that if you add 0 to 3, you still get 3 as an answer, and that is the identity property. Okay, so that one's identity. In part C, this one I think is a little bit easier to pick out which property it is. So how do we get 12 and 36? Well, this is 4 times 3 and 4 times 9 to get 12 and 36. So that 4 has been distributed, so that is the distributive property. In part D, 2/5 times 5/2 equals 1. Again, this just looks like a multiplication problem, but notice that the answer is 1. Right? And notice there's something special about the relationship between 2/5 and 5/2. They're reciprocals. So this is trying to show us that if you multiply a number by its reciprocal, you get 1 as the answer, and that is the inverse property. Okay, and then in part E, some people will jump and say, let's see, distributive here, if you see the parentheses, there are a few that involve parentheses, so look carefully on these. And notice what's different. So I see 6, 7, 3, 6, 7, 3, they're all in the same order, so it's not the commutative property. I don't see actually anything being distributed. I don't see like a 3 times 6 and a 3 times 7 or anything like that. And the distributive property for real numbers that we've proved, it's always a number being multiplied by a sum. You've got to have both addition and multiplication. And in this one, I just see all multiplication. This one is the associative property. What's changed is the grouping, or where the parentheses are. In this first one, we're multiplying 6 and 7 first, and in the second expression, we're multiplying the 7 and the 3 first. All right, and then finally 3 more. In part A, this looks an awful lot like the associative property, but it is not. Okay, so some people will assume that it is because you see these 3 numbers and a parentheses, and those are some of the trademarks of the associative property examples that we've done. But look carefully at what's different. The only change, it's not where the parentheses are, it's that the 6 and 5 have switched places. So again, this is another commutative property one. It just happens to have the 3 tagging along at the end there. How about B? One answer is that this is the identity property. Okay, 1 times anything is itself, but it's actually not. Again, this is the commutative property here too. Okay, so what's different is that the 1 and the 7 have switched places. If we wanted to show the identity property, we would have had 1 times 7 equals 7 to show that 1 times that 7 doesn't change the value of the 7. And then finally, example C. Okay, we have multiplication times a sum. It looks like it's all set up for distributive property, and again, it is not. So your textbook got a little bit boring at the end here with the examples, but I think they really wanted to emphasize just the trickiness that some of these illustrations can take. So what's different about this one? So notice the 6 plus 2, it was at the end, okay, and so it was 5 times that, and now it's 6 plus 2 at the beginning times 5. So we've flip-flopped these two things around a multiplication symbol. Now 6 plus 2 is just a real number, and so is 5. So this is yet again another example of the commutative property. Okay, we switched two numbers around a multiplication sign. And one of those two things just happens to be a little bit longer, the 6 plus 2, instead of writing it as an 8. All right, we haven't done any examples of the closure property, but this one's pretty easy to pick out. Hey, it's more complicated in how we use it, but the only way you're going to see one of these, the closure property illustrated, you're going to see a sentence like 3 plus 4 is a real number. Okay, because that's what the closure property tells us. Just when you add or multiply numbers, real numbers, you get a real number as an answer. It might say something like pi times 15, and then they're just going to copy that same phrase, is a real number. Okay, so it'll be either addition or multiplication, fill in the blanks with numbers, and then we're just stating that it is a real number. And that's it. Okay, so we'll stop there, and next I will go through, I'd like to show you how some of these properties are used. We've already talked about closure and its usefulness, but you do use the commutative, distributive, and associative properties a lot of times when you're trying to do arithmetic problems to simplify things. They're helpful for mental calculations. And then identity and inverse are absolutely crucial for solving equations. So I'd like to look at that as well. So from this video so far, I'm just expecting that you'll have a basic understanding of what the properties are, be able to give examples or counterexamples, and be able to start identifying examples like this as one of these particular properties.